So Unit 2.5, the periodic table, covers some of the sections in Chapter 2, and a lot of the information comes from Chapter 7 in our book. As we found out in Unit 2, much of the information that we found came from early on. The information that was found in Unit 2 through Dalton, Thomson, Rutherford, Bohr, they were doing work at the same time. They were as a group of people that were trying to classify elements for our periodic table. Our periodic table did not always look the way it does. As people believed or looked at, hey, there needs to be a way to classify or easily put together these groups so they're easier to find, they're easier to predict certain properties. They needed a way to do that. Now, 1829, Dobereiner classified it in terms of triads. Triads, groups of 3. Now, many of these triads were grouped based on the fact that they had similar chemical and physical properties. Some of them still exist today. The most notable one is the lithium triad. In 1829, many of the gases were not known about at the time because they did not have a way to separate them as easily as metals were able to be separated. About 30 years later, Newlands begins his quest and gives us a repeating function, that periodic, and proposed what's called the law of octaves. Not sure if that means he was a music person, because octaves, music. They were in groups of 7. The 8th element repeated with the 1st. Now, probably some of why this doesn't work is, again, the noble gases might have only started to become discovered or were not known about at the time. Many of the transition metals do have similar properties to other metals that are in, say, the lithium triad, group 2 on the periodic table that we currently have, and some of the others. And this was obviously, as it says, not correct, but it does give us and gives us a start to the idea of periodicity, meaning a repeatingness. That there might be a pattern of how the elements repeat. Even though Newlands maybe didn't do it perfectly, he at least got us thinking and looking for those patterns. Now, a little bit later, not so long after Newlands, we have Dmitri Mendeleev and Lothar Meyer that independently arranged the elements. And the independently part is an important thing, is that they weren't able to collaborate. Lothar Meyer, a German chemist, Dmitri Mendeleev, a Russian chemist, they didn't have the same ability to network that we have now. And they were able to construct what is viewed as the first true periodic tables. Now, even though both of them did this, Mendeleev is given credit as being the father of the periodic table. And a lot of it comes down to the how he put them together. Both men did a very similar job of doing it. But there was just something different about Mendeleev's that Lothar Meyer did not have. It is actually a tough to find early periodic tables. I think it was a number of about 5 years ago, it was the 100th year anniversary, or 200th, it was around 200 or 150th year of, 150 years of the periodic table. Finding early periodic tables is very difficult. This time in chemistry, if we look back at maybe a timeline of the atom, there is a lot happening with our understanding of the atom that leads us to maybe better understanding and or finding new elements. So finding early periodic tables was very difficult because the periodic table was expanding rapidly as people were discovering new ways to utilize new technology. That because of that expansion and what Mendeleev did to allow for that expansion gives him that ability to be called the father of the periodic table. On that, gentleman. So, what did Mendeleev do differently? Mendeleev used the periodic trends to predict the existence of elements not known yet. That's a big deal. Mendeleev basically says, here are a couple places that you should be able to find, or where you should be able to place elements in the periodic table. We don't know where they are located yet. We haven't found them yet. But here are some of the properties that these elements that have yet to be discovered are going to have, both chemical and physical. It's that allowing for predictability, allowing for expansion that Mendeleev has that Lothar Meyer didn't have. Now, the big part of it, and something that I see a lot of students getting wrong, is Mendeleev's periodic table is based on atomic mass. And I would suggest challenging you to look at your periodic table to see if it still, for the most part, holds true. So if we look closely at our periodic tables, we can see that the current model of the periodic table is not based on atomic mass. This is an example of Mendeleev's periodic table. I don't believe not too many people are fluent in Russian and be able to read all of that, right? If we look at our periodic table and then look at this, we can see there are some things that are very similar. We have hydrogen of 1, lithium, sodium, potassium, rubidium, cesium. They look like they're still together, right? But what's different is these here are in vertical columns on our periodic table, or most periodic tables. On Mendeleev's, they're horizontal. Beryllium, magnesium, and then they go to zinc and cadmium. You know, fluorine, chlorine, bromine, iodine. Okay? Where we have things around here is question marks. Those are the things that Mendeleev suggested. If you look at your periodic table, hint, hint, wink, wink, nudge, nudge. If you look underneath aluminum, you might find an element with an atomic mass close to that of 68. If you look underneath silicon, you might find an element with a mass very similar to that of 70. Those elements are gallium and germanium. Now, even though Mendeleev's periodic table was not perfect, and some elements needed to be switched around here or there, it still allowed for that flow and that predictability. And a lot of it goes unchanged. And it is rationalized by the fact of an inaccuracy in the calculations for the atomic mass of the elements. With the example of cobalt to nickel. Because if we look at our periodic table, the current one that we have, the majority of the elements are in an order of atomic mass. But that is not how it's currently organized. That's not the method that is used. So, in 1913, Henry Moseley concluded that the periodicity was more correctly based on atomic number rather than atomic mass. This led us to what is known as periodic law. And that's the property of the elements reoccur in a repeating pattern when arranged according to atomic number, which we found out last unit. Atomic number, are also known as number of protons. And therefore, the periodic table that we currently use is arranged in orders of periods and groups based on their atomic number, which is the number of protons. The image here gives us a periodic table laid out in the correct order, and the numbering is correct as well. We can see the S and P and the D and the F orbitals or groups from our orbital diagrams that we had looked at in the previous unit.